Aha. Most wonderful good evening, everybody. Let's see if this works. Okay. So, it looks like it might work. Hello. Lovely to see you. I'm not entirely sure if... Oh, I better not get started with trying to pronounce people's names correctly, because that is... If you get it wrong, it's just horrible. And it looks like I've got a little bit of a lag here, but obviously you guys won't notice it, which is a good thing. So I just, for me it's interesting. So I suggest we give people a few more minutes. You made it. Yes, I'm very pleased that you made it. That's really good. Actually, I'm really delighted that people tune in, because I guess this is as new to you guys as it is to your lecturers and teachers. So if things don't go always totally to plan, please have mercy with us. We are basically building the plane as we are flying it. I like that picture. So hello everybody. Are you excited about starting at uni? Flattery gets you anywhere. Well, I hope you will say that also when I've finished with you. Oh, sorry, that came out wrong. Well, there might be some people who are very, very anxious. Um, Being excited and being anxious are two things, although they are quite very much related to each other. But a lot of people feel so anxious about starting something new that they will never try, which I think is a little bit, it's a shame, isn't it? Oh, we've got 19 people already watching, 18 people watching. This is definitely more than we had last week. So that's, is an improvement. While we are waiting, hi Miriam, Mariam, sorry. I need to go to Specsavers. Um, my screen is too small. It's really great. Me and maths have a love-hate relationship. Um, I can see where you're coming from, Bernardo. But actually, if you think about it, treat maths like a language, because it's a very logical. Oh no, okay, scratch that. Try to see maths as sort of a cooking recipe. Yeah, I think that's that. See maths as a cooking recipe. And I tell you why. Yep. I tell you why. Actually, I'll wait a few more minutes. This is called an anticipation loop. But if you have any questions about the course or anything that you're going to embark soon, just quickly post it and I'll try to answer it while we are waiting. So if you've got any burning questions, and I think you had a Zoom meeting with the head of school. Is that right? Will exams possibly be online this year? This is an excellent question to which I don't know the answer 100%. My gut feeling tells me that yes, they will be online. Um, we had them online just this exam season, and I think um, although it wasn't perfect, although it wasn't ideal, It wasn't ideal with the exams, but we are learning, and I think for a lot of students, it's better if the exams are online. And also for the lecturers, there are advantages in having exams online. So yeah, we probably have exams online, but I'm not sure. Oh wow! Goodness gracious, we've got 40 people watching. I'm delighted. And I've just checked, it's only 1 month left before you start. So, yes, I think the exam format was not too bad. And Luxarray, you basically can confirm that it was something useful. Oh, thank you very much. That's really great to to promote the stream. That's excellent because the more people at least watch it a little bit, the better it is. And really, that's really good. Thank you very much. So it's 2030, and probably more people are going to join us. But I thought let's get started with a little bit of really not too strenuous stuff. But I know that these things sometimes cause a bit of problem for students, especially if they haven't done maths for quite some time. And I guess most of you will fall in this category. If I go by my son, Sebastian, big shout out to Sebastian. I think he's just, at the moment, he's at football or something like that. He was supposed to do his GCSEs, and I guess he has done sort of all. So if 2030 as in the time, yes. So if you haven't done a lot of maths, hopefully you will find that useful. I am not mortally offended if people just simply bugger off and say, oh, it's old stuff, but some people might find it useful. Okay, so thank you very much. Big up, Sebastian. That's great. He will love that. I'll show him later when he comes back. Okay, so let's start with something really simple because I want to come back to this thing about the cooking recipes. So let's say we start off with a very simple equation like, say, 5x minus 3 equals, what do we do? Something easy. Equals 32, right? It's a very simple equation, and I guess a lot of people will find that easy. But what I want to demonstrate to you really is sort of the process how we actually solve this for x. And of course, you can put the answer in the chat already, so that shouldn't be too big a problem. But I want to go with you through the formal process, how you solve this, and why I think this is like a cooking recipe. So, anyone got x? What is x? If you haven't, don't worry, because that's exactly what we are going to do now. Okay. Yep. And I see some answers coming in. So how do we deal with it? Okay. Basically, why is it like a recipe? It gives instructions what you are supposed to do. It says basically multiply x by 5 first. Do this first. It's like take 2 eggs and 200 grams of sugar and whisk it with a hand mixer. And then do something else. Add flour. Or in this case, subtract 3 from the result. So, if we look at it, it is 2 parts. The first part here, that is a multiplication. And the second part is a subtraction. And if we want to do it systematically, what we do is we look at it and say, okay, it says first do the multiplication, then do the subtraction. In order to find the result, we need to do it in the reverse order. We need to do then the subtraction if we want to find the result, and after the subtraction we do the multiplication, or rather we do exactly the opposite things. What do I mean? Let me write this down here. 5x minus 3 equals 32. And here comes one of the really important concepts that I want you to never ever, under any circumstances, well, it's good that you count on your fingers. At least you've got fingers. That's a good thing. You know, people from the sawmill would really envy you. But it gets, if it gets a little bit more complicated, then, you know, be careful. Oh, wow, 72. Brilliant. No, 60. Anyway, so what we do is we can do operations, but we must do them to both sides of the equation. This is the requirement. Treat an equation like your twin children. What you do to one, you need to do to the other. So what we can do is, in order to deal with this negative 3 to the subtraction, we do the inverse mathematical operation to both sides of the equation. What do I mean by inverse mathematical operation? Well, just simply the inverse operation of plus is minus. The inverse operation of minus is plus. The inverse operation of multiplication, that's not x, that's multiply, of course, is division. And the inverse of division is multiplication. So what we do is we do the inverse operation to the subtraction. And what we do is we add 3 to both sides of the equation. And I indicate this with these double lines here, with these double lines. In coding, this indicates, if you do coding in JavaScript, this just simply indicates there's a comment. And I indicated that we do the inverse operation to this minus 3 to both sides of the to the equation. So what have we got? We have got 5x minus 3 plus 3 equals 32. And again, we need to do that on that side as well, plus 3. So, what does that give us? Well, on the left-hand side, it gives minus 3 plus 3, and that gives 0. So, we get rid of the 3 on the left-hand side, and on the right-hand side, what we then get is 32 plus 3, and that gives us 35. So on the left-hand side, we have 5x plus 0 equals 35. And we don't need to write the 0. Absolutely right. We don't need to write the 0, we just can simply ignore that. We have 5x equals 35. So now all we need to do is we need to sort of get rid of the 5. And we have a multiplication here. So 5 times x. And all we need to do really is we do the inverse operation of a multiplication. And we need to do that to both sides. So again, here come the double line. So the inverse operation that to a multiplication, that was a division. So we divide both sides by 5. But we can only do that because we have just simply a pure multiplication sitting here. If we had anything else, with a plus or minus sign or something like that, we were not able to do that. We need to have pure operations before we deal with them, especially when it comes to multiplication. So what we can do is we have 5x divided by 5 equals 35 divided by, and we do that exactly again to the left-hand side. Remember, it's like twins. What we will get here is the 5 on the left-hand side actually cancels out. So we have just purely x sitting here. X equals 35 divided by 5. Bernardo, you've got your fingers ready? That gives us 7. Am I right? Good. And it's always a good idea to double check if you've got the right answer. So what we do is we put that into our equation. 5 times 7 minus 3 equals 32. Or let's not write that down. 5 times 7 is 35 minus 3, 35 minus 3 is 37. What should it be? Yes, it should be 32. 32. So we get the same result. So we know tick box proper job done. And the fingers say 7. So if the fingers say 7, it must be right. Yeah, you see the formal procedure, how we are going to deal with things like that. Okay, I want to give you another one, a little bit more challenging. 1 over 8 times x plus 2 equals 0. And now I want you to sort of go through this formalism and check out if you can do it. So I give you a couple of minutes. Always trust your fingers, absolutely. There are lots of things that I could say now. But it's before the watershed, so I'm not saying anything. So find x in this equation here. And try to make use of this formal procedure that I've just showed you. And we will do it together in a minute. Okay, 16, we've got minus 16, minus 16. Yes, I understand it. I'm glad I forgot the minus. That's, that's why we're here. So let's quickly go through it. Yeah. So what we do is, first of all, we need to get rid of this plus sign here. And in order to get rid of the plus sign, we just simply add, or I should probably say, we subtract on both sides of the equation, we subtract 2. So we have minus 2 on both sides. So we get 1 over 8x plus 2 minus 2 equals 0 minus 2. And what we see is we have done the same operation to both sides of the equation. And again, that is absolutely essential. I better not make any comments about the comments. So, what do we get? On the left-hand side, plus 2 minus 2 cancels out. And what we've got left is 1 over 8x equals 0 minus 2. Well, that gives negative 2. So all we have left now is basically a division, because 1 over 8x I can write as x divided by 8 equals negative 2. And we know that I can do the inverse mathematical operation just simply by multiplying with 8. And I get x over 8 times 8 equals minus 2 times 8 Here the 8 cancel out, and what I've got left on the left-hand side is the x equals minus 2 times 8, and that gives us minus 16. I'm so pleased, Thomas. Absolutely brilliant. And tomorrow I show you how you resolve the knot in your fingers. You see? Easy peasy. There are actually quite some interesting apps. I'm trying to find one. Better not risk anything. If you are an iPad user, there's an app called Algebra Touch, where you can practice things like that if you feel a little bit rusty. One of the things that you will photomaths? No. Photomaths, I think photomaths allows you to solve the equation, but what you don't want is somebody doing it for you. Do Algebra Touch. Let me see if I can go to that. Oh yes, here. So basically that shows you, I hope it works. Yes, we are going to cover logs in a minute. So this is Algebra Touch, and you can play around with it a little bit. So you can do, for example, something like that. And it's really a nice thing that you can do. It's cool. You can play around. Okay, now somebody has asked, are we going to touch on logarithms? And I think we should, but before we do that, I would just quickly do yeah, Thomas is still struggling to get his fingers sorted. So let's touch a little bit, before we do the logarithms, let's touch a little bit on exponents. So we are going to work a lot with exponents. So we might have something like 10 to the power of 2, which is, of course, is 100. I don't need to ask you. And just a little bit of terminology alert. This is called, what is the 10 called actually? What's the name for this 10 here? Yep, that's the base. So that's the base. What's the 2? Well, an integer number is just a whole number. It doesn't have to be a whole number, and we will see that in a minute. What is the 2 called? That's the exponent, exactly. And that here, the 100, that is the value. Now, when we are working with these exponents, well, I think this is what they are called, exponent base. But if you have other names for it, I'm not going to argue with it. Now, when we are working with exponents, let's say, for example, 10 to the power of 2 times 10 to the power of 3. Let's say we want to calculate that. And this one here actually means multiplication. So 10 to the power of 2 times 10 to the power of 3. How are we going to deal with that? Well, if we've got the same base, and it only works if we've got the same base, we can write it as 10 to the power of, and here it comes. It's not multiplication. We go one step lower. So multiplication is higher than addition, and there isn't anything below addition and subtraction. So we have 10 to the power of 2 plus 3. That's very important. So the multiply becomes a plus. Does that make sense? Brilliant. If we have, for example, 10 to the power of 2 plus 10 to the power of 4, can we do anything with the exponents? And of course, this would be 10 to the power of 5 now. Can we do anything with the exponents? If we have 10 to the power of 2 plus 10 to the power of 4, we sure can. Okay, what can we do? Well, actually, we can write it out. We can write out 10 to the power of 4 is 10,000 plus 100. And that's all we can do. That gives us 10,100. But we can't do anything with the exponents. So you can't add. If you've got an addition here, there's nothing you can do. Okay? We can also do, say, 10 to the power of 2, and we take the power of that. What does that mean? So basically we have 10 to the power of 2. That gives us 100. To the power of 2 gives us another 100. And that gives us 100 times 100 gives us 10,000. So let's see if we can write this as an exponent. So how many zeros do we have? We've got 4 zeros, so that would be 10 to the power of 4. Can we figure out a rule for that? So if we've got 10 to the power of 2 to the power of 2, we would have 10 to the power of 2 times 2, which is 10 to the power of 4. So we multiply the exponents. Absolutely right. You get it? Just for revision, what is 10 to the power of 0? Is 10 to the power of 1. So 10 to the power of 1 equals 10. Or in general, anything, let's call it a to the power of 0 equals 1. Anything to the power of 1 equals this a. Okay? So, let's say we have 10 to the power of 2 equals 100. 10 to the power of 1 equals 10. 1 and 2 are integers. That means whole numbers. But actually there is no law That's fine, Jordan, don't worry. There is actually no law that says it has to have full numbers. We can also use not full numbers. So, for example, say 10 to the power of, let's say, 2.3. Or let's do 10 to the power of 2.3. It is absolutely spot on. Integer means just a whole number. No fractions, no decimals. So what we can say is this 10 to the power of 2.3, what we can say, it must be a number between 10 to the power of 2, which is 100, and it must be a number between 10 to the power of, 10 to the power of 3, so that would be 1000. So 10 to the power of 2.3 10 to the power of 2.3 must be somewhere in between 100 and 1000. So how do we do that on the calculator? Let's see if I find a calculator here. I've got a calculator. Yep. You probably have a different calculator, but that should not be a problem. So I put in 10 to the power, and that is this yx. And very often you see it with this little roof, 10 to the power of 2.3. Are we allowed to use calculators? Of course you are allowed to use calculators. Do you think I want you to do that by hand? And the answer is, and we've got it here, and I don't even want to pronounce your first name. Sorry if I'm horrible. But the answer is 199.53. So the answer is 199.53. And what we see is our number that we just calculated is indeed between 100 and 1000. It's between 100 and 1000, so we are right. And it gives us a number. Shemek is fine. Brilliant, Shemek. I will remember that. Thank you. Now, one of the questions that we have to answer now is, what if we have something like 10 to the power of x equals, let's say, 2. How do we find this x? And I think Edith's question, and Edith, you are absolutely right. This is where we are going to use this 10 to the power of calculation when we are dealing with pH. And again, Marina and Shemek are right. We use the log function. So what is the log function? I told you that plus is the inverse of minus. Multiply inverse of division. Log is the inverse of something to the power. In this case, let's call it 10 to the power of. So what we can do is we have 10 to the power of x equals 2. And what we do is exactly, no, we don't enter sorcery, it is witchcraft. Get this right, Bernardo. What we do now is we want to get rid of the 10 to the power of, so we do exactly what we've done before. We use the inverse operation, so we use log, and we need to log both sides. So we log 10 to the power of x equals log 2. And what happens now is log and 10 to the power cancels out. like we have seen in the example up here. We get rid of these numbers here. They cancel each other out. So does log and 10. So on the left hand side, we have x equals. Now we've got log of 2. And because our log was to the base of 10, we can indicate it that we are using log 10, because we can use basically any other base. So let's calculate log 2. And your calculator should have a log button. And if there is just log there, it usually means it's the log to the base of 10. So log 2 equals 0.301. So log 2 equals 0.301. So that's our x. Does that make sense? So 0.301. Right. Now let's see, what would we get if we have 10 to the power of x equals, say, 20? Ha! Let's do 20. Can we, first of all, make a judgment where our x must be? And I think this is always a good thing, to make this kind of judgment. So we know that it must be between 1, because 10 to the power of 1 is 10, and 10 to the power of 2 is 100. So our x must be somewhere between 1 and 2. It can't be an integer number, because the integer would be 1 or 2, so it must be somewhere in between. So how do we get this? Well, it's just simply, we take both sides log 10. And then we get log 10 of 10 to the power of x equals, and we need to do it with the other side as well, log 20. Log 10 and the 10 cancel out. We have x on that side equals log 20. And again, this is log 10. So let's see. So let's calculate log 20. Log of 20 equals, oh, it is 1.301. Absolutely right. Equals 1.301. Now, quick reality check. It is, don't worry, Arrhenius is absolutely simple if you get the inroads to it. There is no problem with it. I promise you. We'll do it. So let's do a quick reality check. We got our x 1.301 and we said our x must be between 1 and 2, so that looks pretty good. And you probably noticed we calculated log 2, we got 0.301. We calculated 20, we got 1.301. If we did 10 to the power of x equals 200, if you like to try out, what do we get for x? And Bernardo got it absolutely right. It is 2.301. How come? Well, what you do is you basically can break down 200. You can break it down as 100 times 2. And then what you do is you take the log of 100 times 2. And here comes the rule for working with logarithms. If you got something like that, if you've got log a times b, this is the same as log a plus log b. So the multiplication here becomes a plus. And likewise, if you've got log a divided by b, you get log of a minus log b. Try it out. We said we have log of 200 is log, as I said, log 100 times 2. We can write this as log 100 plus log 2. This is the rule of logarithm, and it derives from the rule of exponents here. Remember, we did the exponents here. When we worked with the exponents, we said 10 to the power of 2 times 10 to the power of 3. We add the exponents here. We had a multiplication in here, but we add the exponents together. So that is why in the logarithms we convert the times, and remember, exponents and logarithms are exactly the opposite operations. So the times here becomes the plus here. Does that explain actually why we get from a multiplication to plus? In a way, you don't need to worry too much about whether you did A-levels or not. As long as you can follow these rules here, it's not a big deal. Can we deal with log A plus B? Absolutely right. Yes. Okay, it is. I come back to that. The 10 to the power of 2 times 2, to the power of 2 to the power of 2. I come back to that in a minute, right? Bear with me. So can we do anything with log A plus B? Remember, we had the case 10 to the power of 4 plus 10 to the power of 2. Could we do anything with 10 to the powers with this one? No, we can't do anything. We cannot simplify this bit here. Absolutely right. So you got it. Hey, you got it. We can't do anything with A plus B. We can only deal with A times B or A divided by B. What about log A to the power of B? What are we going to do with this? Well, under the rules of logarithm, remember we had 10 to the power of, what was it, 2 and 2. And we said we can do that by 10 times 2. The way we deal with that, and Shemek got it absolutely right, we can write this as B times log of A. And the reason is because we have this exponent rule. It's B log R. So log A, I like that. Now, one thing that I want you to remember, And if you've got a calculator, you can try that out. What happens if we've got, log 0.2, and we want the log to the base of 10. Log 0.2, how can we calculate that? I think if you just remember that, then it should be absolutely fine. Don't worry too much with mathematical proofs or something like that. So log 0.2, how can we calculate that? Well, we can write this as log 2 divided by 10. 2 divided by 10 gives us 0.2, right? And we can write this as log 2 minus log 10. Okay, log A is just simply a general expression for whatever base you want to use. And I'll come back to that in just a moment. So, what we can do is log 0.2, log 2. Hey, actually, didn't we just calculate that? No, we didn't. So log 2, would you be surprised if I told you that this is 0.3 roughly? Minus, what was log 10? What is log 10? 1. So we've got 0.3 minus 1, and if I'm not totally mistaken, this gives us negative 0.7 roughly. So log 0.2 equals negative 0.7. Now here's one important thing. Here's one really important thing. The value of a log calculation can be anything. It can be positive, it can be 0, and it can be negative, this value, as we've just seen. Okay? So it doesn't matter. It can be actually any number here. It can be weird numbers. Can the number in here can this be negative? Can this be a negative number? Those of you who have a calculator, try to put in log -1. It is perfect, absolutely right. This can't be a negative number. Can it be 0? Can you get log negative, log 0? What is log 0? It's still maths error, absolutely right. So it can't be 0. So what is in the log here? This log must be bigger than 0. It cannot be 0 or a negative number. The value of whatever you do can be a negative number, and it is a negative number when your log, so if log of x, so this becomes smaller than 0 if this x is actually smaller, so if x is smaller than 1, if x is smaller than 1, then our value will be negative. If x is larger than 1, then the value will be positive. Does that make sense? Absolutely right. Now we were talking about log 10 because we very often have 10 to the exponent of, say, a or whatever. But actually, if you think about it, there is no rule in the entire universe why it should be 10. And people who work with computers, you would find them, actually, they don't work with log 10. They actually work with log 2, which just simply means 2 to the power of whatever. Because they are working with bits, so 0 and 1, which are two states. If you do genetics or molecular biology, very often you work with log 4. So, which means 4 to the power of a. Why 4 actually? Any ideas why 4? Good question, Edith. So what we are talking about, log, if I write it as log 10 with an index here, this means we are doing 10 to the power. So I would write this term here as log 10 of a. So 4, because people got the right idea, we've got A, T, C, and G, the nucleotides. And if we are working with DNA, and we will discuss that, you have 4 different options. So you would work with log 4. And people found out that, for example, the Incas in South America used a different system. Most calculators are set up to do log 10, that's right, and they do a different log. And I'm coming back to that in just 20 seconds. So in South America, the Incas used a different system. They didn't use 10, 2, or 4. Does anyone know what the Incas used? What did the Incas use? And that's still a sort of a mystery why. Nope, they didn't use that. Shemek? Nope, they didn't use 6. They actually used, and nobody really knows why, 12. So 12 to the power of a, which is rather bizarre. Nobody knows why, but we found that out, and it's quite interesting. But again, nobody says that the base has to be a whole number. There's no law in the universe that it has to be a whole number. So you could think of, let's say, log 4.385. So you would calculate everything 4.385 to the power of a, if you were so inclined. And it turns out 4.385 is not a terribly useful number. But what is a very useful number is if you work with log 2.718 and then a long number. This is actually a really strange number, but it turns up a lot in nature, this 2.718. And I will show you in another session how you get this number and where it comes from. This number, 2.718, is actually so common that it has its own name. And you are aware that, for example, pi is 3.1415 and then infinite number. This 2.718 has its also special name and abbreviation. Does anyone know what the abbreviation for this 2.718 is? Yes, it's Euler's number, in honor of the German mathematician Euler. And the abbreviation for that is lowercase e. So if you write log e, this would mean 2.718 and it's an infinite number to the power of a. And instead of log e, people, because this number comes up so often in nature, they write it as ln, the natural logarithm. And you find that on your calculator as ln. And we will do some calculations with ln. but not tonight. Does that make sense? There is also a way how you can convert the logs with different bases, but I suggest, because it is already 20 to 10, I think we are going to call it a day. Edith, this is what it's called in Arrhenius. Exactly, there's the Arrhenius equation, and it makes use of the ln or the e. And this is nothing to be scared of. E just simply is a number like 10, 12, 2, 4.385, 7, 9, 18. And we are going to do some calculations with this E. So, are you happy with that? So what we've done tonight is we covered a lot of grounds. We started with some rearranging of equations. And I showed you the formal mechanism how you do that. We then went on to do a little bit of work with exponents, how the rules of exponents work. And from there, we then worked with the rules of logarithm. We focused on the log to the base of 10, so log 10. But then, and we developed the logs of the rules of logarithm, and these rules actually apply. We did these rules here. These rules apply to whatever the base is. Doesn't matter whether it's 10 or e or whatever number you can think of for the base. And finally, we ended up with figuring out how we do the logs, and we ended up with the natural logarithm. And I think we call it a day. If you've got any burning questions, leave them in the comment section of this video. I will check the comments if you've got any questions, or post them in the group chat, or send me an email, p.klapper. And you've got my email anyway, because the Bioscience admin team has emailed you. So I'm going to bed now. No, I need to empty the dogs first. I'm going to bed, and then I shall see you perhaps next week, where we can do a little bit more. Would you be happy with more of these refresher sessions? Yes, they will be always available. Okay, mic drop. Good night, everybody. Sleep tight and don't let the